Okay, in this video we're going to put everything together, starting with mole conversions and adding in mole ratios, and that is generally this type of stoichiometry problems you'll be facing in the IB papers. So here I have my classic example. I have one bike frame plus two bike wheels makes one bike, but this time I'm giving you the mass of one of each of these different items. So one bike frame is 3 kilograms, etc. I'm also giving you a starting out mass. So instead of telling you how many frames I have, I'm telling you I have 300 kilograms worth of frames. And so this adds a little bit of an extra wrinkle to our problem, where we have to figure out how many frames we have before we can continue with our ICE table. So again, I do that by dividing my mass by my unit mass, and what I get is I get 100 frames and 100 wheels, and obviously 0 entire bikes at the beginning. So again, we're going to go through the changes. So if I was using up all of my frames, I would need 200 wheels. And so I would be left with a negative 100 amount of wheels at the end, which is impossible. So instead, let's try scenario B, where we use up all of the wheels. I only need 50 frames in that scenario, which works because I'd be left with 50 frames left over. What I would end up producing is 50 bikes. Again, this 1 to 2 to 1 ratio. Let's say, for example, I produced really in the lab 50 kilograms of bikes, then my actual yield of bikes would be 10 bikes, and so I could calculate my percentage yield by dividing my actual yield, whatever I actually got when I performed the experiment, divided by my theoretical yield, what I got when I calculated how much I should get based on the masses. So we can do the same thing with a chemical reaction where I'm giving you the masses instead of the number of moles, and so you have that extra little step. And again here, because we're talking about elements, the unit mass is the molar mass, and that can be found or calculated based on the masses in the periodic table. So here I'm starting out with 100 grams of each substance in the reactants. And so what I have to do is I have to convert those grams to moles by dividing by molar mass. And that's exactly what I did here. And so what I end up with is 3.7 moles of aluminum and 0.625 moles of iron oxide. Again, I need to go through my two scenarios and figure out which one limits the reaction. So first I'm going to start out with aluminum. I'm going to pretend that I'm using up all of the aluminum. If I use up all of the aluminum, then I need half the number of moles of iron oxide because it's a 2 to 1 ratio. And so I'll end up needing 1.85 moles, which will give me a deficit at the end of the reaction. I will have negative 1.225 moles of iron oxide, which is impossible. So that scenario where we use up all of aluminum is impossible. Let's try the other scenario where we use up all of iron oxide. In this case, I will need 2 times 0.625 moles because there's 2 aluminum for every 1 mole of Fe2O3, and that works out because I don't get a negative amount of moles at the end. So I can see that my limiting reagent is iron oxide. There's 0 moles at the end, and my excess reagent is aluminum because there's still aluminum left over. And again, I can calculate the number of moles based on that idea of iron. Now the last example I have also has that extra wrinkle, but instead of just being given masses, we have a bunch of different states here. So we have a solution, a solid, and a gas. And so you will be asked to convert between the given units of those different states to moles. So here, for example, I could say I have 300 centimeters cubed of 1 molar HCl and 2.43 grams of magnesium. That would be a question that the IB sets. Now, in order to convert these units into moles, I need to figure out what they are and use the relevant formula. In this case, concentration times volume, because it's a solution, gives us moles. In the case of the solid, we're dividing the mass by the molar mass, and that'll give us the number of moles of magnesium. Now that I have the number of moles, it's the exact same procedure with the ICE table that we saw in the previous video. We're going to take a look at 2 different scenarios. So in our first scenario, we're going to pretend we're using up all of hydrochloric acid, and so what we'll end up needing is 0.15 moles of magnesium, again in that 2 to 1 ratio, and that's impossible because we don't have that much. So instead we're going to look at the other scenario where we use up all of magnesium. So we're going to use up all 0.1 moles of that. In that case, we'll need 0.2 moles of HCl because of that 1:2 ratio. And that works out because we don't have a negative ending amount. We can also identify our limiting and excess reagent based on how many moles are left over at the end of the reaction. And finally, we can determine that there's 0.1 moles of hydrogen produced theoretically. Now, the last type of calculation that the IB can ask you to do for this type of problem is ask you for the volume of hydrogen gas that's produced. And so again, this is a gas calculation. They might give you the conditions at SATP. If they give you the SATP conditions, then you know that 1 mole is 24 decimeters cubed, so you can make that conversion. In this case, it's 2.4 decimeters cubed. They might also just give you the temperature and pressure. If they give you the temperature and pressure, just use PV equals nRT. You have the number of moles, you have the pressure and temperature, and R can be found in the data booklet. Isolate for V and do your calculation.